Okay, this first one up here, what do I want to do with this? Why do I have this tag? Well, this question must have something to do with what we talked about last week, or whenever that was. Why are there ions in the water? Why isn't deionized water? Okay, so one, there's probably ions from the tap. Anything else? How about you? So if this was deionized water and you could somehow keep it deionized after a person got in, then dropping the hairdryer in there wouldn't do anything except make the hairdryer not really work anymore. Not that it would short anything, it was just not designed to operate that slowly. Does that make sense? If the motor isn't spinning at a certain speed, the thing breaks. So water would stop it from spinning that fast. Yeah. Sure, probably. I don't know. Whatever. But what this is about is electrolytes, right? It's the least likely source for sure, the hairdryer. So because you add ions to this water in one way or another, the electricity is allowed to flow. And so the water itself is classified as an electrolyte. So the thing that cracks me up about all this is, why do we have those tags? Because somebody's done that. Every year, several people do that, tag or not. All right, next. Not just do it. I mean, every year people do it, but every year people do it and electrocute themselves. Let's take that a step further. It's not that they just do it, they do it and die. But why the hairdryer company would be on the hook for that, forcing them to put a disclaimer on it and annoy me by making me cut it off, is like ridiculous, right? They've even gone up, the hairdryers are even like 10% more expensive because this is so ridiculous that people do this that they put the GSR breaker on the hairdryer. The GSR breaker is like you go to plug it in and the plug itself is larger and it's got like little buttons on it, like the buttons on those switches. That's so when that does happen, that the hairdryer turns off before the person dies. It has its own circuit breaker. That's how bad this has gotten. What? No, it's too fast. It's too fast. No way. What? It's way faster. It's at the source. The closer you are to where it's happening, the faster the increase is going to be. But that plug right there is not going to pop when one thing goes. That plug is rated for 2 objects of a certain current on them. The plug and the hairdryer is rated for 1 object and 1. So let's say that hairdryer is 15. The plug will be like 10. Sorry. The plug will be 15. The hairdryer will be like 10. So the hairdryer will pop before that breaker ever gets a chance to. What's the best one? This guy would be number 1. Worst one. Worst one. These guys? They're tied. We okay with that? So what is this all based on? What's your explanation? 2 particles. 2 particles. 3 particles. 0 particles, right? Yes.
As long as it's soluble, we start counting them, or is it that if it's more soluble, does that matter?
It matters, but not a ton. Like that vinegar that we had in that video last week, that is what's considered a weak electrolyte, meaning when you put it into the water, they don't fully separate, meaning some of them separate out, but most of them stay stuck together. So there'll be a point where I could put things together like potassium nitrite. That's a bad example. Doesn't matter. Some of the ionic substances don't fully separate out. And so that makes them weak electrolytes. And then we've got ones that the second they hit water, they fully separate. So it's not like they kind of separate out or they don't. It's either 100% separation to be a strong electrolyte, or if they don't separate 100%, then it's a weak electrolyte. It either is or it isn't. If there's any current flow whatsoever, it's an electrolyte. If it's insoluble, it's a non-electrolyte. Yeah, so non meaning no electricity is going to flow whatsoever because I have no ions. So that sulfate would mix with that barium. When that goes into the water, basically the thing just stays stuck together, like chalk would stay stuck together. They don't come apart, so there aren't any ions to do the transport of the electrons. Colligative properties.
How does dissolved substance affect the properties of a solution?
No. So I add a solute, and the properties of the pure substance changes. That's a colligative property. So it's not a solution that I'm adding it to. It's I got this thing, and it's all pure by itself, and I put something in it. How does this new object's properties change? How do they affect the liquid state of substances?
Boiling, freezing, and
There you go. Increase the size of the liquid state, so that would be increase BP, decrease VP. No, sorry, FP. Also, we're going to have a decrease in the vapor pressure. Why is that? Not heavier. It's got nothing to do with mass or weight. The intermolecular forces are stronger, right? So they're less likely to be able to break free of each other. And it's not based off of mass. It's based off of their charge or their partial charge. What happens to why does the boiling point go up? So pretty much the answer to this question. The solute increases overall intermolecular forces. So the intermolecular forces simply become stronger. So then I have to put more energy in. So I have to increase the kinetic energy or the temp to break these stronger intermolecular forces. Salt added to water, why does the freezing point go down? Is there an E at the end of the word disrupt? No? Thanks. Disrupt the what? Exactly. And in crystalline solids, when you disrupt the crystal lattice structure, what happens? Use the right word. Give me the right word. No. What happens to the state of the substance? Give me the right word. No, that's the wrong word. It liquefies. Why is melt the wrong word? Melt is a temp. Even if it's not definition-wise, it infers a temp change or an introduction of heat. In this case, we're not introducing any heat to this. We're just introducing a solute to the solid, and it disrupts the crystal lattice structure, causing the whole solid phase to liquefy. When you're throwing that ice melt on your porch, it's not like you're warming the porch up to cause it to melt. You're just disrupting the solid state. Okay, so we've got a Fahrenheit. I want to know the Fahrenheit temperature. I wasn't very nice with this. Fahrenheit temperature of this 2.5 molar solution. Gave you the equation. Okay, so not completely terrible. So I've got Mg. Oh, got MgCl2. So that gives me an N of 3. Should probably do it like this. Okay. So delta TF is 3, and it's 1.86 degrees C molar, and it's a 2.5 molar solution. This question could be more difficult if I did what? Made you figure out the molarity. Like said, you had this much volume and you had this many grams of stuff, and then you had to figure out go grams to moles and then moles into moles per liter. So it could be more difficult. So let's see, what is this? So I get 13.95 degrees C. So here's the tricky part of this question. What did I just calculate? I calculated the change. So tell me what the new freezing point is in Celsius. It's negative 13.95, which now what do I do? So what do I do? Times 9/5 plus 32. I don't need any parentheses with this because the addition happens last. Times 9 divided by, clear. Negative that. Times 9 divided by 5 plus 32. So 6.89. I'll give you 2, so 6.9 degrees Fahrenheit. Does that make sense? Okay with that? Yeah. Equation. Yeah, absolutely. And the constants. Yep. Sure. Yes, I will. Yeah. What? No, absolutely not. That is a unit that doesn't need to be converted. It's just you should already know that the molarity unit is moles per liter, so then you just need to calculate moles and liters. Yep, that's it.